NASA admits that SpaceX Starship is the most complex machine ever built, and that complexity is causing catastrophic failures. What happens when you stack 33 rocket engines on a single booster and try to make the entire system fully reusable? And why does NASA believe Starship's revolutionary design might be fundamentally flawed? Join us as we reveal the serious engineering problems threatening SpaceX's Mars ambitions and discover whether Elon Musk's team can solve challenges that have never been overcome in aerospace history. Number 1. The unprecedented complexity. SpaceX Starship represents the world's first heavy-lift rocket designed for full reusability, something never accomplished before. Even NASA, the biggest space agency in the United States, acknowledges that this reusable design makes Starship the most complex machine ever constructed. The rocket has faced catastrophic failures, including resonance vibrations, fuel leaks, pressure loss, and engine failures that raise serious questions about whether the project remains viable. After the success of Falcon 9, SpaceX's medium-lift rocket with partial reusability and an impressive 99% success rate, Elon Musk and his team gained confidence to push further. They started developing Starship with much bigger ambitions: full reusability, vastly greater size, thrust, and payload capacity compared to Falcon 9, with the ultimate goal of reaching and landing on both the Moon and Mars. Back in April 2023, during Starship's Flight 1, the rocket exploded, but everyone cheered anyway. Why? Because it survived up to 39 kilometers altitude for 4 minutes before they triggered the flight termination system. This was a proud milestone, especially when compared to other companies that couldn't even get their vehicles above 1 kilometer. For example, Eris, a rocket by Gilmore Space Technologies, a private Australian company, had its maiden flight just weeks ago, but only flew for 14 seconds before losing control and crashing back to the ground. As SpaceX continued with more flights, many ending in explosions, excitement started to fade by Flight 9 when Starship reached near-orbit altitude around 189 kilometers. The more it flew, the more issues appeared. Now SpaceX knows it's time to get serious about fixing bugs and upgrading Starship. Number 2. The engine cluster problem. The challenge begins with the Superheavy booster's 33 Raptor engines. To understand how unprecedented this is, consider the Saturn V rocket that successfully sent Apollo to the Moon. Saturn V was equipped with only 5 F1 engines, producing approximately 7.5 million pounds of thrust total. Using fewer engines significantly reduced system complexity and the risk associated with fuel line management. The exponential increase in complexity with 33 engines immediately surprised NASA engineers, who had never considered such a large-scale engine cluster. Control technologies in the 1960s were not advanced enough to manage such a high number of engines working simultaneously as Starship does today. The engineering challenge of coordinating all these engines to fire, throttle, and shut down in perfect synchronization represents a computational and mechanical feat that was impossible just decades ago. Interestingly, NASA's Space Launch System, developed decades later, uses only 4 RS-25 engines, prioritizing simplicity even more than Saturn V. This design choice likely contributed to SLS's successful ascent to orbit on its maiden flight during Artemis 1. During this mission, SLS reached a maximum altitude of approximately 1,860 kilometers during its main engine burn before its upper stage propelled the Orion spacecraft toward lunar orbit. Does having so many engines automatically make the vehicle less efficient? Not necessarily. Superheavy has successfully landed multiple times on Mechazilla using only its 2 central Raptor engines. This controlled landing was once pure science fiction because rockets like SLS and Saturn V usually exploded or ended with ocean splashdowns, never returning intact like Starship's booster. Number 3. The reignition challenge. However, there's one major challenge. The engine control system is extremely complex. Historically, rockets were designed to fire their engines just once on the launch pad, burning until fuel was spent. But reigniting rocket engines mid-flight is a completely different challenge that introduces multiple failure points. Rocket engines are inherently unstable. While ignition on the pad happens under ideal conditions with ground support systems monitoring every parameter, doing the same in flight where conditions are dynamic and less predictable can easily lead to catastrophic failures. Adding to the complexity, the Raptor engines used on Starship have a notoriously difficult startup sequence. Each Raptor uses two separate turbopumps, one for liquid methane and one for liquid oxygen. These pumps must spin at incredibly high speeds to feed propellant into the pre-burners, where a small portion of fuel is burned with an igniter torch to generate high-pressure hot gas. This gas then drives turbines that spin the pumps even faster, creating a self-sustaining cycle. Because of this design, precise timing and synchronization are absolutely critical. The consequences of losing multiple engines during critical flight phases could be catastrophic, as the vehicle might not have sufficient thrust to complete its maneuvers or achieve its trajectory objectives. Number 4. Fuel flow solutions. This problem still appears occasionally, such as when a booster loses one or two engines during the return burn. Fortunately, this hasn't significantly affected overall performance because the system can compensate through engine-out capability, and the tower catcher has successfully caught the booster multiple times despite occasional engine losses. This redundancy is one of the advantages of having so many engines, as losing a few doesn't necessarily doom the mission. SpaceX addressed the fuel flow challenge by adding a giant fuel transfer tube inside the Superheavy version 3 booster. This massive component acts like a reservoir, helping regulate and balance fuel flow evenly to all 33 Raptor engines. The engineering behind this system is remarkable, as it must handle cryogenic propellants at extreme temperatures while maintaining structural integrity under the enormous forces of launch and landing. Thanks to this innovation, the booster can perform complex maneuvers like belly flops and mid-air flips for landing without any fuel interruptions. However, the bigger challenge for Starship lies elsewhere, in conditions far more extreme than anything the booster experiences. Number 5. The re-entry weight crisis. The real challenge for Starship lies in stability during atmospheric re-entry, where it encounters extreme conditions at speeds of tens of thousands of kilometers per hour. Many NASA experts believe the vehicle's enormous size increases its exposure to these harsh conditions, while its tremendous weight contributes to inherent instability, leading to frequent failures. While this design difference holds the potential to revolutionize space travel by enabling larger payloads and eventual Mars colonization, it also brings significant engineering challenges. Weight is the fundamental problem. Even with disposable rockets where recovery isn't a concern, after companies optimize vehicle weight, engine efficiency, guidance systems, and everything else, only about 2 to 3% of a rocket's liftoff mass reaches orbit. That leaves almost no margin for error. If your rocket is even slightly heavier than designed, you simply won't reach orbit. This extreme challenge is why only a handful of countries have successfully flown spacecraft into orbit despite decades of attempts. This mass fraction problem becomes exponentially worse when you try to make a vehicle reusable. Traditional expendable upper stages can be built as light as possible because they only need to survive one flight. Starship must survive not just the initial launch, but also the brutal conditions of re-entry and landing, then be ready to fly again within weeks or even days. Number 6. The heat shield dilemma. Building a fully reusable upper stage makes weight optimization exponentially harder. The energy that must be dissipated during re-entry doesn't increase linearly with velocity. It increases with the square of velocity. This means that as Starship returns from orbit at approximately 27,000 kilometers per hour, the kinetic energy converts into heat at an alarming rate. This energy turns into heat, causing Starship's temperature to spike into thousands of degrees Celsius, making it glow white-hot like a meteor. You can't make the upper stage as light as a traditional rocket without it burning up completely during re-entry. To protect against these extreme temperatures, the exterior is covered with approximately 18,000 ceramic heat shield tiles. But these tiles are very heavy, adding significant mass that reduces payload capacity. Each tile must be individually manufactured, tested, and attached to the vehicle's skin with precise positioning to ensure complete coverage. Internal support struts needed to keep the spacecraft structurally sound through turbulent re-entry further add significant weight. The vehicle experiences enormous aerodynamic forces as it plows through increasingly dense atmosphere, creating stresses that would tear apart a lightly built structure. These reinforcements are essential, but come at the cost of reduced payload capacity. This creates strong pressure to minimize the mass of both the heat shield and structural components as much as possible. The key is carefully calculating how much weight can be reduced without risking catastrophic failure. Engineers must walk a tightrope between making the vehicle light enough to carry useful payload and heavy enough to survive the journey. SpaceX has done quite well with Starship Block 1, successfully reaching space and executing controlled landing in the Indian Ocean. But one critical thing it hasn't done is deploy meaningful payload to orbit. Number 7. The payload problem. Some critics argue that SpaceX may be pushing weight reduction too far, potentially making the rocket more fragile than it should be. Even vibrations and structural stresses from flying with only a fraction of the expected payload could cause damage or failure to the vehicle. They also implemented vent holes designed to prevent pressure buildup in enclosed spaces and introduced a new nitrogen purge system designed to better prevent propellant leaks by maintaining positive pressure in fuel bays. According to SpaceX, these upgrades provided some improvements, but Flight 8 still encountered other technical issues that led to vehicle loss. Later, SpaceX identified the most likely root cause of the failure as a hardware problem in one of the center sea-level Raptor engines on the upper stage. This issue likely involved either a fuel leak or overheating, both problems that can arise if an engine is built with minimal structural margins or operated beyond its designed limits during flight. The dry mass of Starship's upper stage is over 20 times greater than that of Falcon 9's upper stage. To match Falcon 9's performance in terms of payload-to-orbit capability, it would theoretically need about 20 times the thrust, assuming the same specific impulse or fuel efficiency. Even if the Raptor engines perform exactly as advertised, with each engine producing roughly 3 times the thrust of a Merlin 1D engine used on Falcon 9, the 6 Raptors on Starship's upper stage generate about 18 times the thrust. That's impressive engineering, but still slightly short of fully compensating for the increased mass, leaving performance margins tighter than ideal. Number 8. The Block 3 breakthrough. Many experts and observers expect that Starship Block 3 will address these challenges to a significant degree. This upcoming version will feature the new Raptor 3 engine, anticipated to improve both performance and reliability substantially. But as Elon Musk explained, Raptor 3 is designed to operate without a base heat shield, leaving the engine exposed to the plasma environment during re-entry. Any leaked fuel would simply burn harmlessly in the surrounding plasma throughout the flight rather than accumulating in dangerous concentrations. This design philosophy represents a radical departure from traditional aerospace engineering. In contrast, the current Raptor 2 design encloses the engines within a protective bay, making any leaks far more dangerous. Fuel can accumulate in the enclosed bay where it can't escape, increasing the risk of fire or explosion when it reaches ignition temperature or encounters an ignition source. The Flight 8 failure likely resulted from exactly this scenario, where leaked propellant ignited within the confined engine bay. The upcoming Starship Block 3 promises to address the remaining issues from Blocks 1 and 2 and bring humanity closer to establishing a permanent presence on Mars. With improved engines, better structural design, and lessons learned from multiple test flights, Block 3 represents SpaceX's best attempt yet at achieving the fully reusable heavy lift capability that has eluded aerospace engineers for decades. NASA scientists admit that SpaceX Starship is the most complex machine ever built, with 33 Raptor engines creating unprecedented control challenges and a reusable upper stage struggling with weight versus heat protection trade-offs. The question is, can Starship Block 3 with its new Raptor 3 engines solve fundamental problems that have caused catastrophic failures, Or has SpaceX pushed reusability beyond what current technology can achieve? Drop your thoughts in the comments. And if you want more coverage of SpaceX's engineering battles, make sure you're subscribed. Thanks for watching.